The United States has 93 nuclear reactors. They generate about 20% of all U.S. electricity, more than solar and wind combined. Most Americans couldn't name a single one, and almost no one knows that those 93 reactors aren't all the same. There are fundamentally different designs running right now, each with a different history, a different risk profile, and a different future. Today, we're covering every type. Pressurized water reactor. The pressurized water reactor is the workhorse of American nuclear power. 70 of the 93 operating reactors in the United States are PWRs. The concept is straightforward. Uranium fuel rods heat water under extreme pressure, around 155 times atmospheric pressure, so that water never boils. That superheated water flows through a steam generator, where it heats a separate loop of water that does boil and drives a turbine. The two water loops never mix, which means the radioactive water stays contained. PWRs were originally developed for nuclear submarines. The first one, USS Nautilus, ran on a PWR in 1955. The design was then scaled up for commercial power. Plants like Palo Verde in Arizona, the largest nuclear plant in the country, run 3 PWR units, generating enough electricity for 4 million homes. The defining advantage of the PWR is its safety profile. If pressure drops, the reaction slows down automatically. It is the most widely deployed reactor design in the world. Boiling water reactor. The boiling water reactor takes a simpler approach. Instead of 2 separate water loops, the BWR lets the water in contact with the fuel rods boil directly and sends that steam straight to the turbine. Fewer components, simpler design, and a lower operating pressure than the PWR, which sounds like a safety advantage. It isn't always. The steam that drives the turbine in a BWR is mildly radioactive, which means the turbine hull itself requires radiation shielding. The United States has 23 operating BWRs, including the Quad Cities plant in Illinois and Browns Ferry in Alabama, the largest BWR plant in the country. The BWR design became internationally infamous in 2011. Fukushima Daiichi in Japan ran BWRs. When the tsunami knocked out the backup generators, the cooling systems failed, and 3 reactors melted down. The accident didn't happen because the design was fundamentally flawed. It happened because the backup power was placed in a flood zone. But it accelerated the retirement of BWRs across the U.S. Several have closed since 2011, and no new BWRs have been ordered in decades. AP1000. The AP1000 is what the nuclear industry calls Generation 3+. It's a PWR, but redesigned from the ground up with one goal: passive safety. The AP1000 doesn't rely on pumps, valves, or operator intervention to cool the reactor in an emergency. It uses gravity, natural circulation, and stored water tanks above the reactor. If power fails completely, the laws of physics keep the reactor cool for 72 hours without anyone doing anything. There are exactly 4 AP1000 reactors operating in the United States. Units 3 and 4 at the Vogtle plant in Georgia. They are the only new nuclear reactors built in the U.S. in the last 30 years. They were originally supposed to cost $14 billion and open in 2016. They finally came online in 2023 and 2024. The final cost, $35 billion. The overruns weren't caused by the reactor design. They were caused by a construction industry that had forgotten how to build nuclear plants after a 30-year gap. The AP1000 is now being exported to China, where 4 units are already operating and performing well. Small modular reactors. Small modular reactors don't exist in the United States yet, but they may define what comes next. The idea is to build reactors small enough to manufacture in a factory, ship by truck or rail, and install on site. A traditional reactor produces around 1,000 megawatts. An SMR produces 50 to 300. The pitch is that factory manufacturing eliminates the on-site cost overruns that destroyed the Vogtle timeline. NuScale Power had the first SMR design approved by the NRC in 2022. Then its first project, a 6-unit plant in Idaho, was canceled in 2023 when projected costs doubled. TerraPower, backed by Bill Gates, is building a sodium-cooled fast reactor called Natrium in Wyoming, currently scheduled for 2030. X-Energy is developing a pebble-bed reactor that uses fuel embedded in graphite balls. The Pentagon is separately funding micro-reactors small enough to power a forward military base. None of these are generating electricity yet. The SMR concept is real and technically sound. Whether it can be built cheaply enough to compete is the question the entire industry is waiting to answer. High-temperature gas reactor. The high-temperature gas reactor never made it in America, but it came close. Instead of water, HTGRs use helium gas as the coolant. Instead of conventional fuel rods, the fuel is embedded in graphite moderator blocks, allowing operating temperatures far higher than water-cooled reactors. Higher temperatures mean higher thermodynamic efficiency and the ability to produce industrial process heat, not just electricity. The United States built one commercial HTGR, Fort St. Vrain in Colorado, which ran from 1979 to 1989. It was shut down after persistent mechanical problems with its helium circulators. Not a reactor design failure, but an engineering execution failure. The concept survived. China brought an experimental pebble-bed HTGR online in 2021. The U.S. Department of Energy has funded research into advanced HTGR designs, and X-Energy's pebble-bed reactor mentioned earlier is an HTGR variant. The design is considered among the safest ever conceived. A pebble-bed HTGR physically cannot melt down because the fuel geometry prevents it. It just hasn't been commercialized at scale. Fast breeder reactors. Fast reactors are the reactor type that was supposed to solve nuclear power's fuel problem forever. A conventional reactor uses less than 1% of the energy available in uranium. A fast reactor, using fast neutrons rather than slowed-down thermal neutrons, can use more than 90%. And it can breed new fuel while it runs, converting non-fissile uranium-238 into plutonium-239. In theory, the world's existing uranium reserves could power civilization for thousands of years. The U.S. built and operated experimental fast reactors for decades. EBRY in Idaho was the first reactor in the world to generate usable electricity in 1951. EBR-2 ran for 30 years. The Integral Fast Reactor program at Argonne National Laboratory demonstrated passive safety so convincingly that in a 1986 test, engineers intentionally shut off the cooling pumps, and the reactor safely shut itself down without any operator action. Congress canceled the IFR in 1994, 3 years before completion, on non-proliferation grounds. The concern that the plutonium it produced could be diverted for weapons. The technology worked. The decision not to pursue it was political, not scientific. Fusion. Fusion is not fission. Every reactor discussed so far splits heavy atoms apart. Fusion combines light atoms, hydrogen isotopes, and releases far more energy. No long-lived radioactive waste, no meltdown risk, effectively unlimited fuel from seawater. Physicists have known how to do it since the 1950s. The problem is containment. Fusion requires temperatures of 100 million degrees, hotter than the core of the sun, and no material can touch plasma that hot. In December 2022, the National Ignition Facility in California achieved fusion ignition for the first time in history. More energy out than laser energy in. It was a genuine scientific milestone, but NIF uses lasers, not a practical power plant approach. The main commercial path is the tokamak, a donut-shaped magnetic containment vessel. ITER, the International Tokamak being built in France, is the largest science project in human history. It is behind schedule and over budget. Commonwealth Fusion Systems in Massachusetts is building a smaller, private tokamak using high-temperature superconducting magnets that didn't exist 5 years ago. They expect to demonstrate net energy gain by 2027. If it works, the first commercial fusion plants might operate in the 2040s. Fusion has always been 20 years away. For the first time, the reasons to believe that might actually be true are real. The United States chose one technology in the 1970s, built most of its fleet, and then stopped for 30 years. The reactors running today are approaching the end of their licensed lifespans. 93 reactors, most of them, built between 1970 and 1990, generating 20% of American electricity. The designs that could replace them, AP1000S, SMRs, fast reactors, eventually fusion, are either just getting started or not yet built at all. The gap between what nuclear can do and what nuclear is doing has never been wider. Which type surprised you most? Drop it in the comments and subscribe because next time we're going even deeper.